Hello guys, so in this video we're going to be discussing chapter 18, which is a chapter that talks about aldehydes and ketones. I'm going to divide this chapter in three big sections. So I'm going to discuss first section 18.1 through 18.5. Then we're going to discuss 18.6 through 18.11. And then we're going to finish with 18.12 through 18.15. All those sections are going to be discussed in this video, okay? So let's get started with section 18.1. The agenda for this section, basically, we're gonna go over the nomenclature of aldehydes and ketones. We're gonna talk about the structure and bonding of the carbonyl group. We're gonna talk also a little bit about the physical properties, the source, the common source of aldehydes and ketones, and we're gonna go over some previews and reviews of some chemical reactions that produce aldehydes and ketones, or where ketones and aldehydes are involved. So let's start with the nomenclature for aldehydes. Aldehydes and ketones are extremely common examples of carbonyl groups or compounds. As I mentioned before, when we're talking about the infrared spectra, there is a signal that is around the 1700 for the carbonyl group. And if that strong signal is there, that means that we have some kind of compound that has a carbonyl group that could be a ketone or an aldehyde, or also could be an anhydride. It could be an carboxylic acid, or a bunch of all different kind of compounds that have this carbonyl moiety on the compound. So the aldehydes and ketones, that's what they have in common. In this chapter, we're going to discuss the structure and bonding of the carbonyl group. We're going to go over some nucleophilic additions as a paradigmatic reaction of carbonyls. We're going to go over some examples of reactivity. And finally, we're going to talk about spectroscopy signatures of aldehydes and ketones in NMR, proton, carbon, also in infrared spectrum as well. Here, this molecule is called formaldehyde, is an aldehyde. Whenever you see a carbonyl, which is the carbon double bond part, and in one of the sides you see a hydrogen, that's going to be automatically an aldehyde. If it has two hydrogens, as is in this case, this is known as formaldehyde. This one, when you have the carbonyl group, when an alkyl attached in one side and the hydrogen in the other one, this one is known as an aldehyde. And when you have two alkyl groups attached to that carbonyl, you have a ketone. Those alkyl groups, they can be the same. If they're the same alkyl group, you're going to have a symmetric kind of ketone. If they are different, then you're going to have a non-symmetrical or unsymmetrical ketone. Let's gonna talk about the nomenclature of aldehydes and ketones. Aldehydes contain the formyl group, which is the carbon double bond oxygen and hydrogen. That part is known as the formyl group. They are named by replacing the E of the alkene that we have, alkane, with the al. Okay, so it's gonna be known as alkanal. If it's methanol or methanol, it says propane is going to be propanol, as if butane, butanol. So the Al is going to be added, and it's going to replace the E of the hydrocarbon. Here we have one molecule, one structure. As we have learned before, we need to look for the longer chain that has or contain the functional group. The functional group in this case is this carbon. Remember, guys, this is a carbon double bond oxygen. So this carbon is part of the main chain. Okay, so we're going to count 1, 2, 3, 4, 5 carbons. This one is one chain of 5 carbons. We can start against 1, 2, 3, 4, 5 to evaluate the other methyl groups that are in this position. 1, 2, 3, 4, 5. So any of these 3 methyl groups are going to give a chain of 5 carbons. So we're going to choose basically the one that is basically straight. So we're going to take this group in here. Let me see if I can. Yep. So we're going to take this chain in here. And as we can see there are 2 methyl groups that are breaking that bubble. So these are 2 substituents. So we have 1, 2, 3, 4, 5. 5 is pentane, but it's because it's an aldehyde, it's pentanol. and we have two methyl groups in position 1, 2, 3, 4, two methyl groups. So it's going to be 4,4-dimethyl pentanol. So we have 4,4-dimethyl pentanol. The 4,4 due to the two methyl groups that are in this carbon here, which is carbon number 4, 1, 2, 3, 4, and the pentanol 5 carbons in the main chain, the longest chain, and is an aldehyde. So that looks at this one. We have in here this chain, and here basically we have 6 carbons, and in the last two carbons, carbon 5 and 6, we have a double bond, which is an alkene. So we have 1, 2, 3, 4, 5, 6 hexane, but it's an aldehyde, hexanal, but it's a double bond, so it's hexanal. Okay, so in that case, we're going to mix different things that we have learned previously and that need to be part of that name. So position 5, 1, remember this carbon, guys, of the carbonyl group 1, 2, 3, 4, 5. Here is where the double bond started. So it's 5-hexanal. That could be one name, or also you can use this other name when you split it, X-hex 5-enol as well. So any of these two ways is good in that sense to name this compound, okay? So 5, because the double bond started in carbon number 5, xen, and then the end is going to be al because it's a aldehyde, okay? So let's look at this one. In this one, we have a bunch of things and looks pretty scary, but it's pretty simple, okay? So let's focus. Here we have an aromatic group, and this aromatic group is going to be basically a substituent of the main chain. Remember, the carbons of the carbonyls are going to be part of that main chain. So we have there 4 carbons, okay? It's butane, okay? Butane, and then we have a phenyl group that is here. This is a substituent. The aromatic ring is a substituent of the main chain. And we have 2 aldehydes. So it should be di-al. Al is the ending, but because we have 2, we use di. So it's going to be 1, 2, 3, 4 butanediol. Okay, butanediol. And this one is going to be the position 1, 2. We can choose any of those carbonyls to be number 1, but because we need to put the numbers in a way that the substituent has the lower number, we're going to choose this as number 1. If this were number 1, then the substituent will be number 3. So that's why we choose this one, because it's going to be position number 2, which is a lower number than 3. So it's going to be 2-phenyl butanediol, okay? 2-phenyl butanediol. So we have the butane here and the diol because of the 2 aldehydes. Rings with the formyl substituents are named as carbaldehydes, okay? Carbaldehydes, if you have a ring and you have an aldehyde attached to that, a formyl group attached to that ring, that's going to be a ring carbaldehyde. So for example, here we have a 5-member ring. That's what is called cyclopentane, okay? So that's going to be the name of the ring, cyclopentane, and then we add the word carbaldehyde, okay? Carbaldehyde. So cyclopentane carbaldehyde, that's going to be the name of this compound. Also, we can have other type of rings as aromatic rings or fused rings. As for example, this one is naphthalene. Okay, so it's just naphthalene, and the formyl group is attached to position number 2. So that's what is 2-naphthalene carbaldehyde or naphthalene 2-carbaldehyde. So naphthalene here again is the name of all this unit in here. This is the naphthalene, the 2 fused rings. And the carbaldehyde basically is the formyl group that is in here, okay? So 2-naphthalene carbaldehyde. And then to number the cycles, the bicycles is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that's why it's 1 and 2. There's 1, this is 2, and there's going to be the formyl group attached to that position number 2. Note that the formyl group does not need a locand. You don't have to assign a number to the formyl group. What do you think is that? Why we don't have to give a number to the formyl group? Very good. The formyl group is going to be at the end of the chain, and we can count that as a one. So always going to be at the end of the chain and always going to be that one position. So it's basically is going to be always the one. So you don't have to assign. You can have an aldehyde in the middle of a chain because it's going to be then a ketone. It's not an aldehyde. To be an aldehyde, it needs to be at the end. And because it's going to be at the end, that position always going to be number one. So that's why you don't need to number that aldehyde or that formyl group. Also, we have some common names that are acceptable in UPAC for some specific aldehydes. This one is known as formaldehyde, which is the formyl group with the two hydrogens in each side, also known as methanol. We have also another that is known as acetaldehyde, ethanol. This one has a methyl group in one side and the hydrogen in the other one. That's why it's an aldehyde. And we have benzaldehyde. We talk about this, or we name it when we're talking about the aromatic groups and chapters before, and we were naming those aromatic rings. And one of them has this formyl group, which is basically the benzaldehyde. So this is known as a benzaldehyde. Aldehydes take precedence over alcohols. So if you have an alcohol in the same chain as an aldehyde, the aldehyde is going to go over in ranking than the alcohol. And the alcohol is going to be used as a substituent, so it's going to be known as an hydroxide. Remember that alcohols as substituents are known as hydroxide. So for example, we have this in here. We have 1, 2, 3, 4, 5. We have the chain of 5 carbons. So that's why it's going to be pentanol, okay? And then we have 1, 2, 3, 4, 5. The hydroxy group is in position number 5. So that's why it's known as 5-hydroxypentanol. 5-hydroxypentanol. Also, we can have a ring, which can have also a formyl group, and this is known as carbaldehyde. Remember the carbaldehyde, cyclohexane, because it's basically a ring of 6, cyclohexane carbaldehyde. And also we have an hydroxy group in position number 1, 2, 3, 4, 1, 2, 3, 4. Either way is going to be number 4. So it's going to be 4-hydroxy cyclohexane carbaldehyde. Now, these two groups are in opposite faces of that cyclohexane. So that's what known as trans. They are in opposite faces. This is looking up and this one is looking down. So that's why it's trans 4-hydroxy cyclohexane carbaldehyde. And this one is using the aromatic ring and the formyl group, which is known as benzaldehyde. All this group here is benzaldehyde. And we have this hydroxy group in a para position. The P is for para, ortho, meta, para. So it's going to be para-hydroxy benzaldehyde. Para, position 4, hydroxy benzaldehyde. And that's going to be for the aldehydes. So let's talk a little bit about the nomenclature of the ketones. To name ketones, we're going to basically substitute the E is going to be replaced of the alkane with the O-N-E, one. Okay, but it's going to have another kind of sound, but it's going to be one. It's going to be the ending of the ketones. So the carbonyl carbon is given a locant, smallest possible carbon in cyclic, and the cyclic carbon is going to be, or cyclic ketone is going to be carbon number 1. In chain, you need to give the location of that carbonyl group because you can have that carbonyl group in different places in a chain. Okay, and the aldehydes always going to be number 1, but in a ketone, you can have different kind of options to put that carbonyl group in that chain. So that's why you need to give the locant of that carbonyl group. In the cyclic ketones, that ketone's always going to be in carbon number 1, okay? So for example, here we have a chain that is this one in here. In that chain, we can have, for example, 1, 2, 3, 4, 5, 6 carbon. So it's hexane, basically. And we're going to change that E by 1. So it's 3-hexanone, okay? 3-hexanone, 1, 2, 3 hexanone. Now, if the carbonyl group were here instead of there, that will be in position number 2, starting from this point, that will be 2-hexanone. So that's why it's really important for us to give the to give the locand to each carbonyl group, okay? Because in the ketone is going to be different as in the aldehyde. In the ketone, that carbonyl could be in different carbons in the same chain. So that's why we need to give the specific locand of that carbonyl group. Here we have another one. This one is going to be basically, let me look for the pen. Sorry, here I am. So it's going to be 1, 2, 3, 4, 5 carbon. The chain is going to be 4, 5 carbon. Here we have a substituent that is outside of the bubble. So that's a methyl group. It's in position 1, 2, 3, 4. Remember, this one is in position number 2. This is carbon number 1. 1, 2, 3, 4. 4-methyl. The carbonyl group is in position number 2, 4-methyl 2-pentanone. Or you can also name this as 4-methyl pentan 2-one as well, or methyl 2-pentanol. In here, we have a ring that has a carbonyl group on it. It's a ketone, so that's part of the ring, and that makes this carbon number 1. Okay, remember, there's going to be carbon number 1. So we have 1, 2, 3, 4. In the position number 4, we have the methyl group, 4-methyl cyclohexanone. Okay, the same thing. Instead of cyclohexane, is going to be hexanone because we have a ketone as part of that ring. That ketone is part of the ring, and this carbon is going to be carbon number 1. We don't have to give that location in that sense because it's going to be always number 1 in a ring, okay? In a long chain, open chain is going to be different. In open chain, you need to assign a specific number to that carbonyl bar, but in a ring, it's going to be always carbon number 1. Aldehydes takes precedence over ketones. If we have a molecule that has both functional group, the ketone and the aldehyde, and we need to name that molecule, the aldehyde is going to be more it's going to be more rank than the ketone. Okay, it's going to have more priority in that sense. So, for example, we have something like this. This one has 1, 2, 3, 4. We have here an aldehyde, and here we have a ketone. So this one is going to be more important than the ketone in the sense of the nomenclature. We have here 1, 2, 3, 4 carbon chain. So it's going to be butanol, okay, butanol. And we have a ketone in position number 3. The carbonyl as a substituent is known as OXO, OXO, okay? And we have that in position 1, 2, 3. So it's going to be 3-oxo-butanol. That's going to be the name of this compound, 3-oxo-butanol. 3-oxo, position 3. The carbonyl group is going to be known as an oxo. Butane, because we have 4, and al, because it's an aldehyde. And as we mentioned before, it's going to be carbon number 1. Always the aldehyde is going to be carbon number 1, so you don't have to assign a specific location to that aldehyde. Always is going to be 1. Ketones can also be named using functional class nomenclature as alkyl-alkyd ketones. So as we did with ethers, we can, for example, we can call this ethyl propyl ketone. Okay, we have an ethyl on this side, we have a propyl on this side, so it could be named ethyl propyl ketone, and that's also acceptable in that case as the nomenclature of a ketone. We have also some common ketones. One of them is known as acetone. This one is basically really known and common. It's used as a remove nail polisher. So this acetone is a ketone. We have 2 methyl groups attached to that carbonyl. This one is acetophenone. That is also a ketone attached to basically a phenyl group. And we have the benzophenone, which is a carbonyl group with 2 alkyl groups in each side, which are aromatic rings. So benzophenone is another one that is also pretty common. And those are the common names for them. So let's talk about the structure and bonding of carbonyl groups. The carbonyl group is a carbon double bond oxygen kind of group. And to be a double bond in a double bond of carbon and oxygen, or any double bond, always you're going to have one bond that is going to be a sigma bond and the other one that's going to be a pi bond, okay? In any multiple bonds, one of them always going to be sigma, the second or the third are going to be pi, okay? So you have three triple bond, one is sigma, two are going to be pi bonds. If you have a double bond, one is going to be sigma and one is going to be pi, okay? So in the carbonyl group is the same concept. We have double bond between carbon and oxygen. Those bonds, one is going to be a pi bond and the other one is going to be a sigma bond. Also, the hybridization of this carbon is going to be sp2, okay, because it's has a double bond. That means that because it's sp2, the geometry of this part of the molecule is going to be planar, okay? It's going to be planar, it's going to be flat. So all the carbonyls in ketones and aldehydes, in carboxylic acid, whatever molecule has a carbonyl group, that carbonyl group is going to be flat, so it can be attacked with a nucleophile if from two faces, okay, from the front or from the back side. And also because it's a carbonyl group, you're going to have there a dipole moment that is going to be due to the difference in electronegativity between the oxygen and the carbon. That's why then the oxygen is going to pull more electrons or those electrons closer to it, making the carbon a partial positive and the oxygen partial negative, creating that dipole. And that dipole is really important, as we're going to see a little bit later in the physical properties, and also in reaction that gave a lot of reactivity to that carbonyl group, that dipole moment in that structure. So the carbonyl group, or the carbonyl carbon, is sp2 hybridized, as I mentioned before, with a trigonal planar geometry and approximately 120 degrees bond angle between the bonds of that carbonyl group. Okay, so here we have formaldehyde. This is flat. This is the carbonyl group, oxygen, carbon, hydrogens in each side. And the angle between the bonds is approximately around 120 in each side. This one is going to be a little bit lower, is 116. This is going to be larger. And why do you think is that? Why do you think that here we're going to have basically an angle a little bit bigger than in here? Because the effect of the lone pair of electrons of the oxygen is going to repel the bonds, or the electrons are in the bond, pushing those bonds closer to them, and that's why they have a 116.5 angle instead of 120, okay? Because in here, we have here a larger electron density, and that's going to make repulsion between the electrons that are in the bond, pushing them and getting closer together, in this case, in the bottom. Same kind of behavior we see here in the acetaldehyde. Okay, acetaldehyde. In this case, here the angle is going to be larger because we have 3 hydrogens in here. We're going to have a larger repulsion here, and that's why the angles get closer in between in this side. Okay, because here we have the lone pair of electrons, and here we have the 2 electrons in here, but also 6 electrons in here around in this carbon, because we have 3 bonds in there that has 2 electrons. Okay, so those 6 electrons are also high density, and this is going to have a lot of repulsion in this side, so that's why the angle here is larger, around 124. And if we have an acetone, for example, so the acetone basically is 120, 121 over 120, the same concept. This lone pair of electrons are pushing those methyl groups downward, getting these bonds closer as in here, okay? And maybe you ask, yes, but they're not as closer as here. What do you think? Very good, because we have here also hysteric hindrance, and that's going to make repulsion, and it's going to it's not going to allow them to get so closer. And also they're going to have electron density that is going to be having some repulsion as well in the bottom. So that's why, even though we have in both sides that pushing, but also we're going to have that repulsion going backwards from the bottom and not allowing that to get closer to, let's say, 115, for example. Okay, very good. Let's talk about the bonding and polarity. The 2 bonds in the carbonyl are sigma bond and a pi bond, as I mentioned at the beginning, analogous to the carbon double bond carbon in the alkenes, okay? So we have here ethylene, that is a carbon double bond carbon, And we have the bond length of this carbon is 134 picometers. And the bonded dissociation energy to break this bond, you need around 730 kilojoules per mole or 172 kilocalories per mole. Okay, this is basically the energy that you may need to break this bond. If we compare that to formaldehyde, which is basically the same kind of structure, because we have here the carbonyl group, that is a double bond carbon oxygen. We have a double bond carbon in here. This one, the length of the bond is 121, is shorter than in here. Here we have carbon double bond carbon, carbon double bond oxygen. Why do you think that in here we have a shorter double bond than in here? The effect of electronegativity of the oxygen. Very good. And that way, the oxygen is going to, as we know, is going to pull those electrons closer to him, and that's going to make those bonds to get shorter. Okay, though that's going to make those atoms to get closer because the oxygen is pulling those electrons toward him. So that's why the length of those bonds is shorter than the, for example, double bond carbon carbon. Okay, the energy to break this bond carbon oxygen also is a little bit larger than the one of the double bond 748 or 179. We're talking about kilocalories units per mole. So once again, those electrons has been pulled by oxygen. So you need to apply a little bit more energy to break that bond as compared to the carbon double bond carbon. The two bonds in the carbon double bond oxygen are also, as I mentioned, sigma and pi. However, the carbonyl bonds or the carbon oxygen bonds are strongly polarized toward oxygen, leaving carbon with partial positive charge. This one here is 1-butene. So this one is a double bond carbon-carbon in here. And we compare that to, for example, propanol. We have here our oxygen carbon. We can see a higher electron density in here. The red zone represent higher electron density in this kind of representation. So we have here a dipole moment. This side is basically partial negative, and this carbon in here is going to be partial positive. Okay, making that bond a basically dipole in there, and it's going to be a polar bond that we're going to have in there. And that's going to give us a lot of possibilities when we're talking about reactions, because a nucleophile can attack this carbon in here because that carbon is partial positive, or if we are in the presence of an electrophile, that electrophile can interact with the negative part, which is going to be the oxygen of that carbon. Okay, so we have there the dipole moment in the carbonyl group due to the difference in electronegativity. The oxygen is pulling those electrons closer to the electrons closer to oxygen. So in the presence of a nucleophile, it could be an anion or a lone pair of electrons. Bonds, they're going to bond to the carbonyl carbon, okay, because the carbonyl carbon is going to be the partial positive. And as we know, the nucleophile that has higher concentration of electrons or has charge of negative charge as well. So that negative charge is going to be attracted by the positive charge of the carbon of the carbonyl. If they are in the presence of electrophiles as protons or Lewis acids, then they're going to bond to the carbonyl oxygen. They're going to make their interaction with the oxygen of the carbonyl group. Because electrophiles has less electron density, they're going to be most of the time positive or partial positive, and with a deficit of electrons. And here we have a higher density of electrons. That's why there's the interaction with an electrophile is going to be with the oxygen. The interaction of a nucleophile is going to be with the carbon, both of them from the carbonyl group. So let's talk about the physical properties of ketones and aldehydes. Aldehydes and ketones experience strong dipole-dipole forces. As I mentioned before, they have this difference on electronegativity between the carbon and the oxygen of the double bond of the carbonyl group, and that's going to create this dipole moment. That dipole moment is going to create the interaction, strong forces of dipole-dipole interactions, okay? So that means that boiling and methyl points are generally higher than alkenes of comparable molecular weight. Alkenes or alkanes, remember the only kind of intermolecular forces that they have is the van der Waals interaction basically in that sense. So they don't have really strong intermolecular forces. So that's why the alkenes and the alkanes, they are really volatile if you compare that with aldehydes and ketones. And eventually, if we compare that with for example, alcohols can make hydrogen bonds with are pretty stronger kind of interaction. We need to apply more energy in a way to break those kind of hydrogen bonds. So for now, boiling and melting points are lower than related alcohols. However, why? I just basically explained that. So even though they have a dipole-dipole force, which is pretty strong between them, their boiling point and melting point is not going to be as higher as the alcohol because they are lack of hydrogen bonds. Okay, the hydrogen bonds in alcohols, they make that interaction between them stronger. That's why the boiling points and melting point are larger as compared as aldehydes, ketones, or alkenes. So this 1-butene, for example, the boiling point is -6 degrees. For propanol, which basically has the same kind of molecular weight, the boiling point is 49. Basically, we're talking about more than 50 degrees Celsius difference between this molecule and this molecule. And if we compare that with propanol, which is basically the alcohol, there's going to be basically around 50 degrees difference between the alcohol and the aldehyde. And this is because of the presence of hydrogen bonds that the propanol can do with themselves, while the propanol, they can do dipole-dipole moments, and that's going to give them a little bit strength between them more than alkenes or alkanes. Okay, so that's why they have a pretty higher boiling point than the alkene in this sense. Source of aldehydes and ketones. So far, we have been seeing a few examples of different reactions that produce aldehydes and ketones. Nature produces aldehydes and ketones as well, usually via oxidation of alcohols. This is one of the aldehydes that we have basically in our bodies that's known as ondecanol. It's a sex pheromone of greater waxmood. Also, we have another kind of molecule is the civetone, which is obtained from scent glands of African civet cat. We have the jasmone and also another one that is fragrance, that is the citral. These are basically you can find them in essential oils of the jasmine or the lemongrass oil, this too. So here we have a ketone, we have an aldehyde in here, we have a ketone in here, we have an aldehyde in here. So these are different kind of ketones and aldehydes that nature produce in that sense. In the lab, we can produce as well this type of compounds, specifically with the reaction of alcohols and carbonyls are extremely versatile. Okay, so for example, if you have a ketone, from a ketone, you can produce an alcohol. Okay, going through reductions conditions. Okay, from a ketone or an aldehyde, you can use any kind of some kind of reduction agent that's going to produce an alcohol. Now, from the alcohol, you can go to the ketone or the aldehyde through oxidation reactions. It's going to be the opposite of the reduction. It's going to be oxidation. So when you want to produce an aldehyde or a ketone from an alcohol, you need to have oxidative condition. If you want to go from the ketone and the aldehyde to any alcohol, it's going to be reduction. So that's why redox reaction of alcohols and carbonyls are extremely versatile. Aldehydes and ketones can be accessed from almost any carbon oxygen oxidation level. For example, a reduced then oxidized method is useful for aldehyde synthesis from carboxylic acids. So from the carboxylic acid, you can reduce the carboxylic acid to an alcohol, and then you can oxidize that alcohol to produce the aldehyde. So if we see this example in here, the carboxylic acid can go through reduction conditions and produce the alcohol, and then the alcohol can be oxidized to produce the aldehyde. So we have here benzoic acid in the presence of lithium aluminum hydride and water. That's going to reduce the benzoic acid to benzyl alcohol. And then using a mild condition of oxidation, we can produce the aldehyde. Remember, if you use here strong oxidation, what is going to happen? What product we're going to obtain in here instead of the aldehyde? The carboxylic acid. So we're going to back to benzoic acid. So that's why we can use PDC or PCC. Okay, those are kind of mild conditions of oxidation, and that will stop the reaction in the aldehyde, no going forward to the carboxylic acid. If you use the dichromate kind of oxidation conditions, then you're gonna get the carboxylic acid. Ketones can be prepared from aldehydes via Grignard addition followed by oxidation. So you can have an aldehyde, add a carbon. Remember, the Grignard is going to be an alkyl group with an organometallic kind of end, and that's going to add that change to the aldehyde, making a secondary alcohol. And then you can oxidize that secondary alcohol to a ketone, and you're going to obtain that product as well. So the Grignard addition forms an intermediate secondary alcohol, and then that alcohol can be oxidized using chromic acid to produce the ketone. In this case, the chromic acid is not going to take the secondary alcohol to the carboxylic acid. It's going to be just one oxidation that produce the ketone. So basically, we have here the aldehyde. We have here the Grignard reagent, the organometallic reagent. We're going to add this R group to the carbonyl group, producing the secondary alcohol, and then oxidize this alcohol to the ketone with basically chromic acid as well, and they're going to have the ketone as a product. So here we have, for example, this Grignard that's going to basically add 1, 2, 3, 4 is butane, I think. Yep, 3, 4. It's going to add a chain of 4 carbons, creating, and then with the acid, the alcohol. So from the propanol, you obtain the eptanol, 3-eptanol, and then that eptanol can be oxidized with chromic acid to obtain the ketone. In this case, 3-heptanol. Okay, we have the 3. In this case, 1, 2, 3. Heptanol got to be 7 carbons. So once again, aldehyde in the presence of a Grignard addition, and then we can add an oxidation conditions to obtain the ketone. Other reactions, as we saw before, that can produce carbonyl groups as ketones and aldehydes. Remember when we talk about in section 812, the ozonolysis of alkenes, we break this double bond and we add an oxygen in each end, and that will produce a ketone and an aldehyde, or 2 aldehydes, or 2 ketones, depending on what we have as R in here. So for example, we have this double bond in the presence of ozonolysis. We're going to break it, and we're going to have the ketone, acetone in one side, and we're going to have the aldehyde in the other one, as is in here, okay? So by breaking the double bond with ozonolysis, we also can produce ketones and aldehydes. Also, the hydration of alkynes. Remember the hydration of alkynes, when we have alkyne and water in acidic condition, we're going to produce what first? Who remember what is the intermediate here? When we add here water and in the presence of acid, it's going to be an alcohol with a double bond. And the name of that species is what? An enol, okay? An enol, but the enol is really unstable, and it's going to tautomerize to the corresponding ketone, which eventually is going to be this one, in this case, 2-octanol, okay? So we're going to create here an enol in this position, an OH and a double bond. That's going to be my intermediate, and that one is going to basically tautomerize to the corresponding ketone. That's going to be the 2-octanol. So the triple bond octane in the presence of water and acid is going to produce the enol and then tautomerize to the corresponding ketone. That's the hydration of alkynes, another way that we can obtain also carbonyl groups. We also can do Friedel-Crafts acylations of aromatic compounds. In here, we have the aromatic ring in the presence of this acyl halide. And then we can add this group to the aromatic ring to produce then the ketone attached to that aromatic ring, okay? So here we have, for example, 1-chloro-2-phenylethane, the presence of butanol chloride. This one is going to be attached to the carbon. It's going to nucleophilic attack in here. There's a Lewis acid that is going to coordinate with the oxygen, making this carbon more electrophile. And then this carbon is gonna basically attack in here to make the substitution in that carbon. As well in here, we can use an anhydride and also the same thing. This one is gonna attack in here, add in this part of the anhydride, and there's gonna be acetic acid is gonna be produced at the end in the acid workout. And here we add this, all this chain, okay, it's gonna be added in here. And that's gonna be my product. So the Friedel-Crafts acylation of aromatic compounds as well is another way that we can produce ketones. And also by oxidation of primary and secondary alcohols, as we mentioned before, if you oxidize a primary alcohol on mild conditions, you're gonna have an aldehyde. If you oxidize a secondary alcohol, always you're gonna produce the ketone. So primary alcohols in the presence of PDC or PCC are going to produce the aldehyde. Secondary alcohols in the presence of chromate is going to produce the ketone. Okay, so in secondary alcohols, you can use strong oxidation agent as chromate to produce the ketone. If you use this in here, we're going to obtain then the carboxylic acid. It's going to be oxidized as well. We have another hydrogen here that can be oxidized, and that's why we add here the OH to produce the carboxylic acid in that sense. That's why with primary alcohols, we're going to use mild oxidative conditions as PCC or PDC. So that was basically a review of the different reactions that we have learned that produce ketones and aldehydes. So let's learn a few different now, section 18.5. This is going to be basically a review and a preview of the past reaction of carbonyls. We have seen several reactions of ketones and aldehyde previously. So for example, reduction to alkanes using Wolff-Kishner or Clemmensen conditions is going to reduce that carbonyl group to a ketone or an aldehyde. Also, the reduction of alcohol, catalytic hydrogenation or metal hydride reduction is going to produce also the ketone of the aldehyde on this condition are going to produce those alcohols. And also nucleophilic additions, the carbonyls of the ketone and aldehydes in the presence of organometallics or lithium alkyls groups as well. They're going to be basically attacking the electrophilic part of the carbonyl group of any aldehydes or ketones. These two last reactions in particular illustrate that carbonyls engage in nucleophilic additions at carbons. So we will examine the reactivity of other nucleophiles in the next section of this chapter. So for now, let's basically go over this. Remember, this is going to be basically something that is in general the model that you should have in your head when we're talking about carbonyl groups. This carbon is going to be partial positive, oxygen partial negative, dipole moment because of the difference of electronegativity. That means that if I have an electrophile, that electrophile is going to interact with the oxygen. And if we have a nucleophile, that nucleophile is going to attack the carbonyl, the carbon of the carbonyl. So that's why here we have the Y, that is a nucleophile attached to the carbon, and the X, which is the electrophile attached to the oxygen, that is the nucleophile in the carbonyl group, okay? So that's going to be always the same kind of structure that you should have in your mind when we talk about the reaction of carbonyl groups. So in summary, UPEC names of aldehydes and ketones are developed by identifying the longest continuous chain that contains the carbonyl group and replacing the final E of the alkane of the corresponding alkane by Al for aldehydes and O or 1 for ketones. The carbonyl carbon is sp2 hybridized, and it and the atoms attached to it are coplanar. So that part of the molecule always going to be planar due to the sp2 hybridization of that carbon. Aldehydes and ketones are polar molecules. Nucleophiles attack the carbonyl group at the carbon, and electrophiles react with the oxygen of the carbonyl group, okay? So because of that dipole moment, you have two possible places where you can have reaction. The carbon with any nucleophile can attack it, And the oxygen that's going to be a good nucleophile can react with an electrophile that they can find. Aldehydes and ketones have higher boiling points than hydrocarbons, but have lower boiling points than alcohols, okay? They have lower boiling points than hydrocarbons because they can have dipole moments. The hydrocarbons don't have that. They just have van der Waals type of interaction, which are pretty weak as compared to the dipole-dipole. And the alcohols, they have hydrogen bonds, which are stronger kind of intermolecular interactions as compared with a dipole-dipole interaction. And that's why the alcohols can have a higher boiling point than the ketones or aldehydes. There are numerous reactions that yields aldehydes and ketones discussed in earlier chapter. Ozonolysis of alkenes. Remember, you can obtain from one alkene if both have alkyl groups. You can have a ketones. If one of them has a hydrogen, one is going to be an aldehyde and the one's going to be a ketone. Or if both but has hydrogen, both carbons of the double bond, when you split it, you're going to have two aldehydes, okay? Ozonolysis, that's H8.12. Also, the hydration of alkynes. The hydration of alkynes is going to produce an enol as an intermediate, and that enol is going to tautomerize to the ketone, corresponding ketone. You're going to have that as your product. For the craft of aromatic compounds as well, you're going to have the aromatic ring in the presence of an alkyl halide, and that's going to basically interact with the presence of a Lewis acid is going to make that alkyl halide a good electrophile that's going to be attacked eventually by the aromatic ring. We have also the oxidation of alcohols. Oxidation of primary alcohols is going to give you aldehydes in mild conditions, and oxidation of secondary alcohols is going to give you ketones. And that basically will be all for that first section. So let's go now for section number 2, which is going to be basically covering sections 18.6 through 18.11. And here we'll be discussing the principles of nucleophilic addition, hydration of aldehydes and ketones. We're going to also learn about the formation of cyanohydrine, reaction of alcohols, and how they produce acetyls and ketones. And acetyls and ketones can be used as protecting groups, and this is a really, really important reaction that we're going to learn today. And also we're going to learn of reaction with ketones and aldehyde with primary amines to produce imines. And finally, the reaction of secondary amine to produce enamines. So let's go over section 18.6, principles of nucleophilic addition, hydration of aldehydes and ketones. So as we mentioned before, a ketone and an aldehyde, they have a carbonyl group, which has the characteristic to be a dipole, to have a dipole in that region due to the difference of electronegativity between oxygen and carbon. Water, in other hand, also is polar. We know that water has the oxygen is going to be partial negative and the hydrogen is going to be partial positive. So that means that the oxygen of water can be a good nucleophile. And because we have a carbon of the carbon that is a good electrophile, they can attack that carbonyl group. That's going to be basically the addition of water to the ketones or aldehyde. Water acts as a nucleophile toward ketones and aldehydes. The addition of OH and hydrogen across the carbonyl group is called hydration. So one OH is going to be attached to the carbon, and when we split this single bond, now that lone pair of electrons is going to be attack one hydrogen, and you're going to have an alcohol in here, as well as an alcohol that basically attack to this carbon. So you can have a diol in that two alcohols in that same carbon. It's a geminal diol. That process is known as hydration because you add a molecule. In total, you add a molecule of water, one OH and one hydrogen. When you combine them, you have water. So you add a molecule of water to that carbonyl group. The hydration is often very rapid. We are often interested in equilibrium constant for this process. Now, the question is a ketone really a ketone or is mostly a hydrate in water? because this reaction is pretty fast, a ketone, if we have a mixture of ketone and water, really we're going to have a ketone there, or we're going to have the diol, the hymnal diol? That's the question, okay? So that's basically the hydrate. So the ketone in the presence of water, this is going to be the product, okay? It's going to be the hymnal diol or the hydrate. It's the same thing, okay? And this is going pretty fast. The constant for this equilibrium is going to be the product over the reactant. The product is going to be the hydrate. The reactant is going to be the carbonyl group. It could be ketone or aldehyde. The value of the constant of hydration is governed by intuitive structural effects. We're going to go over that in the next couple of slides. So aldehydes versus ketones. Ketones are hydrated to a much smaller extent than aldehyde. That means that aldehyde are more reactive than ketones in the presence of water. So aldehydes really are going to have this kind of composition where they have another molecule of OH with them. Inductively donating alkyl groups stabilize the carbonyl carbon, making hydration disfavorable. If we think about it, the carbonyl groups in a ketone, they are electron donating. So they're going to give an electron density to the carbon. And we knew before that the carbon usually in a carbonyl group is a good electrophile because their oxygen is removing electron density. But now the carbons are given more electron density to the carbon, so that makes less electrophile that carbon as compared with an aldehyde. So that's why the aldehydes are more reactive than the ketones, okay? Because in the case of the ketones, that carbon that is how you call it, is a target, okay, for nucleophiles because it's partial positive due to the pulling electron density of the oxygen. Now the methyl groups or the alkyl groups on the side of the ketones are donating electron density to that carbon, making that carbon a little bit less reactive than, for example, aldehydes. So here we have formaldehyde. We have hydrogens in here. Oxygen is pulling electron density. The hydrogens are not giving that much electron density to the carbon. So this is a good electrophile. Then we have acetaldehyde in here. This methyl group is donating, okay, electron density to the carbon, making this carbon a little bit less electrophilic than the formaldehyde. And when we compare with acetone, we have two alkyl groups donating electron density to this carbon, making this carbon less electrophilic than acetaldehyde than formaldehyde. Now, remember, that doesn't mean that this doesn't experience the reaction, okay? It's going to experience the reaction, but less than formaldehyde or acetaldehyde, okay? So that doesn't mean, oh, no, this you're going to have just acetone and water. No, you can have sometimes the hybrid form of acetone and water as well, okay? But as less quantity as compared with formaldehyde. So increasing stabilization of carbonyl group, decrease the constant of hydration. So this one is going to have a smaller hydration constant as compared with the formaldehyde. Formaldehyde is always going to have a higher constant of hydration. Other electronic effects. So for example, electron donating alkyl groups stabilize carbonyl carbon and decrease the constant of hydration. An electron withdrawing group, such as perfluoroalkyl, make the carbon more electrophilic and increase the constant of hydration. So if the alkyl groups that you have in each side of the carbonyl group of a ketone, they have something that can withdraw electron density. Now they're going to make that carbon more electrophilic through any kind of nucleophilic addition, okay, or attack. So increasing stabilization of carbonyl group, once again, decrease decay of hydration, as we saw before. But however, you need to have in mind that depends also on the groups that you have in those alkyl groups of the carbonyl that can withdraw electron density, making that carbon more positive. So if we have just alkyl groups on both sides, they're going to donate, making that carbon less positive. Okay. If you have something that remove it other than the oxygen, then those with electron withdrawal groups are going to make that carbon more reactive. And that's why it's going to have a higher constant of hydration. What about the steric effects? Large alkyl groups tend to disfavor addition. Why? Because the steric effect is going to make hard the attack of the nucleophile to that carbon. Okay, so also the structural part has a really important part in this kind of reaction. Addition brings group from 120 degrees bond angle to smaller of 109.5 degrees bond angle, increasing steric crowding. Remember what we saw before when we were looking at the angles, okay, that when we have alkyl groups also, they get closer because of the tendency of a higher electron density with compared to the oxygen at the top. So that's also going to cause steric crowding, and the nucleophile is going to make harder to attack to that carbon. So we have here the hydrate form of hydrate or formaldehyde, acetaldehyde, and also the acetone here. So acetaldehyde is, they can, okay, have some kind of hydrate compounds. This one is going to be hardly any hydrate present in water due to that water needs to go through here, and this two methyl group is going to make harder that water to attack that carbon. But as I said before, it's not like they are not going to attack. Some of them are going to have the ability to skip all those methyl groups and attack, but it's going to be the less as compared, for example, with formaldehyde. Formaldehyde, you can have a lot of them, most of them are going to be basically hydrated as compared with acetone. So let's talk about the mechanism of hydration. We can have two types of mechanism of hydration. One, which is basic, and the other one, which is going to be acidic. So let's start with the basic catalyze. The hydroxide, which is a base, serves as a nucleophile and adds to the carbonated carbon, forming an alkoxide intermediate. So for example, this is a classic example of nucleophilic addition to the pi bond. So we have here the hydroxide. We are in basic condition. So this is one of the species that you will find. As we mentioned, this is partial positive, partial negative. So the oxygen is going to attack, okay, the carbon of the carbonyl group. And then we're going to need to break one of these bonds because we can keep 5 bonds in carbon. And that is going to be converted in a double lone pair of electrons in here. And there you're going to have an alkoxide ion intermediate. Okay, this one is an alkoxide. You have the alcohol. And then what we can do next? Very good. We can protonate this with what? We're in basic conditions. We don't have acids, but we have what? Water. And water can act as an acid even though in basic conditions. Okay, so we can remove an hydrogen from water. And if we remove an hydrogen from water, we're going to produce what? OH, which is basically the species that we have here as a basic catalyst. Okay, so we have OH that's going to be produced by doing that deprotonation of water. So the second step, the alkoxide deprotonates water, regenerating the base. So we have here the alkoxide, we have a molecule of water going all around. Remember, when we put a reaction there, aldehyde plus water, you don't have one-on-one. You have thousands and thousands of thousands, especially water that is a solvent. You have millions of those molecules in there. So one of them is going to attack in here. You're going to have another one available in here to remove that hydrogen and then create OH, and then protonating that alkoxide in here to create a diol in that side. So we're going to have the geminal diol, okay, and also the hydroxide that we can use eventually to attack another molecule of the aldehyde or the ketone, okay? So that's how we produce the geminal diol in basic conditions or basic catalyst. What about the acid catalyst? Okay, so in acid catalyzed hydration, the acid protonated the carbon and the oxygen. Remember, the carbon, now we have positive hydrogens. So we need something that is a nucleophile in the carbonyl group. What part is going to attack that positive part? The oxygen. The oxygen is more electronegative than the carbon, created that dipole here negative. So this one is going to basically attack the hydrogen. And then the hydrogen is going to, those electrons are going to be going to the oxygen to create water, which is neutral in acidic condition. That's perfect. And then we're going to have this part that's going to be protonated in here. Sorry, I need to connect my computer in here. Was basically lowering the battery. So We have here the protonation. We have the OH in here. We have the water. Now, what can happen in here? The carbon can attack in here, stabilizing this double bond of oxygen. Water adds to the carbonyl atom. So now the water can attack this carbon, which basically can eventually create this lone pair of electrons to stabilize this positive charge. And we have here the conjugated acid of geminal diol. So we have the two alcohols in here, but this one is protonated. So what we can do next? We can remove this hydrogen with what? What base we have in an acid catalyst condition? Water. Okay, so remember, water can act as an acid or as a base depending on the conditions that you have of the reaction. So protons transfer from the intermediate back to water. We have here the protonated geminal diol. Water can remove this hydrogen. Remember, nucleophile to electrophile. There's the electrophile. We're going to attack that electrophile by remove that hydrogen, and we're going to have then the geminal diol and the hydronium ion. And that's going to be the acid catalyzed hydration, the two mechanisms for the hydration of aldehydes or ketones, basics, and acidic conditions. Let's go now to section 18.7, cyanohydrin formation. Cyanohydrin formation. So the addition of CN and hydrogen across the carbonyl from a cyanohydrin forms a cyanohydrin. Okay, so cyanohydrin is the formation of this CN attached to the carbon and also a OH. So here we have aldehydes are ketone. Both of them can undergo this reaction. Hydrogen cyanide, and then we can attach this part to the carbon, and the hydrogen can attach to the oxygen. And this right here is the molecule known as cyanohydrin. Cyano of this and hydrogen with the OH in here. Now, HCN is rarely used. Instead, MCN is used followed by acidic workup. So MCN, as we mentioned before, why we use a metal in here instead of use HCN? Who remembers? This, if you compare this to this is an ionic compound, remember? Because the metal is a cation and this carbon is an anion. And the anion has a charge, a negative charge. So this metal makes this a better nucleophile than in here, because in here, he already has that negative charge. So in here, this carbon can attack directly to this carbon in here and create eventually the cyanohydrin, okay? So that's why we use the salt of HCN, because this salt is more reactive than HCN for this type of reaction, okay? Remember that. And eventually we use the acidic workup so we can regenerate or produce the OH in here, protonate that part. Mechanistically, nucleophilic addition of CN is followed by protonation of the former carbonyl oxygen. So we are forming here also a new carbon-carbon bond, okay, between the carbon of the CN and the carbon of the ketone or the aldehyde. Thermodynamics and equilibrium. Trends in equilibrium constant for cyanohydrin formation mirror those for hydration to some degree. So here we have a ketone. The constant for hydration of ketone is 14. When we compare that to benzaldehyde, look at this constant of hydration is higher because this is an aldehyde and this is going to be more reactive than this one. This is stabilized by these two methyl groups. That's going to make this less electrophilic than in here, okay? Then if we look for this one is 1.7 times to the power of 4, okay? The formaldehyde has a lot of this in the hydrate form as comparing to this one. And formaldehyde is going to be 10 to the 5th, power 10 to the 5th, okay? So in this case, most of the time we're going to have formaldehyde in the hydrate form than formaldehyde itself. That's what it means. General aldehydes and anhydride ketones give good yields of cyanohydrins, okay? So by using this, knowing this, we know that aldehydes, basically, and non-hydride ketones, they're going to be good substrate for the cyanide to attack and produce the cyanohydrin, okay? So in that case, we're going to take that as an advantage because they're going to be pretty reactive, and then they're going to react with the cyanide to produce the cyanohydrin. Now, let's go and see the reaction of alcohols with another functional group known as, the reaction of ketones and aldehydes with another functional group, in this case, going to be the alcohol. We saw first the cyanide, now it's going to be the alcohol, and see what products we can obtain when we react the aldehydes or the ketones with alcohol. This is a nucleophilic addition as well, okay? Alcohol, OH, that oxygen is nucleophilic. We have a polar bond in there, and that has two lone pairs electron. They can attack any nucleophile. So nucleophilic addition of an alcohol to an aldehyde should produce a hemiacetal, okay? The hemiacetal is going to be the product of the addition of alcohol to an aldehyde. So we have the aldehyde in here. When we react with water, this is the product, which is an hemiacetal. The hemiacetal, we add the OH of the water, and we have the OR of the alcohol attached to the same carbon. The OR of the alcohol to the carbon, and the protein of the water or the alcohol as well is going to be attached to the oxygen that was previously of the carbon group. This group in here is known as an hemiacetal. Now, that one eventually is going to turn to the acetal. This group is really unstable, okay? So this carbon is going to react with another alcohol and produce 2OR, and this is known as an acetal. So when alcohol react with aldehyde, the main product is going to be always an acetal. That's going to be the main product, okay? So when water react with aldehyde, it's going to go through hemiacetal, but eventually it's going to produce the acetal. And also water. Okay, so this is basically the formation of the acetal, aldehyde, alcohol, hemiacetal, alcohol again, and the acetal plus water. Usually this intermediate is not isolable. It reacts further to form an acetal. Analogous products from ketones are called ketones. Instead of acetals, they are known as ketones. Acetal formation is often thermodynamically favorable. Keto formation usually is not. For the same reason as we mentioned before, this aldehyde, okay, has this carbon that is a little bit more electrophilic than the carbon from a ketone because we have two electron donating groups, reducing that electrophilic characteristic of that carbon in the carbonyl. So that's why thermodynamically, this is more favorable than the ketone or the keto, formation of the keto. So the formation of the acetal has the mechanism as well. We use acid catalyzed addition of ROH. It's similar to dehydration. So we have here benzaldehyde and ethanol in HCl. We're going to have eventually the benzaldehyde ethyl hemiacetal. Okay, we have going to have here the hemiacetal. From here, nucleophilic substitution of OR or OH occurs via an acid promoted SN1 mechanism. So the protonation now of the alcohol through this ethyloxonium ion, which is basically the alcohol protonated. We're going to have this water, which is a good living group. And now this water can leave and this action can attack. So that's going to be basically our next step. So OCH3 can create a double bond in here, making this water to leave. And we're going to have there a ketone, basically with the alkyl group attached in here previously, the one that can attack from the alcohol. So we'll have a double bond in here, oxygen positive. And this can be stabilized by resonance structure, making the carbocation in here and the oxygen with no charge, because usually oxygen with a positive charge really, really unstable. But because of the resonance, we can stabilize this by the production of this carbocation, which is a benzylic carbocation, which is pretty stable. This carbocation can go in the ring and get stabilization or get stabilized. And then this carbocation then eventually can be attacked by another molecule of alcohol to produce the basically acetal in there. So here we have the molecule of alcohol attacking the carbonyl and producing here the acetal. We're going to remove this hydrogen in the next step, but here we have the two ethoxy groups attached to this carbon, conjugated acid of benzaldehyde diethyl acetal. Resulting is the conjugated acid. The protonation basically is the last step of the intermediate by alcohol to give the acetal product. And I think that's no. So in here, we just basically remove this. Going to be the next group that we're going to remove is going to be the hydrogen with, it could be another molecule of alcohol or water if we have also in the medium. And then we're going to remove that, producing the acetal in that molecule. Let's now convert acetals to carbonyls. Excess alcohol is usually used to drive acetal formation toward products. Excess of water can be used to drive this reaction back toward the carbonyl, okay? So this is an equilibrium type of reaction. The acetal in the presence of water is going to produce acetone and alcohol. So because it's an equilibrium, we can play with the conditions in a way to drive this reaction one way or the other way. If we add more water, we're going to drive this reaction to the aldehyde or the ketone. If we add more alcohol, we're going to drive this reaction to the acetal form, okay? So that equilibrium between the ketone and the acetal can be manipulated by what we add. If we add more water, we're going to drive that to the acetone or to the ketone of the aldehyde. If we add more alcohol, we're going to drive that to the acetal. It is quite easy to interchange carbonyls and acetal because we can control those conditions of adding more water or adding more alcohol. 18.9, acetals and ketones as protecting group. So this is one of the main role of an acetal product is going to be the protection of certain functional groups in a molecule. At a late stage in synthesis, we have to be careful not to destroy functional groups we've installed previously. For example, alkylation of an acetylide ion will not work for this type of transformation. Let's say that we have this. If we use here an acetyl ion, this is not going to happen because it's going to attack in here. This is really reactive. Okay, so we're going to have some of them that are going to produce this, but also some of them that are going to attack in here, doing the making a tertiary alcohol. Okay, so that's why now we can protect this. Okay, we can make an acetal in here, and then we can do the reaction and then remove the protected group, and it's going to be still be there the carbonyl group. Okay. So the carbonyl group react with strong nucleophiles. Carbonyls are base sensitive. They're really sensitive because they have this dipole-dipole moment. They have that carbon that is good electrophile, the oxygen that is a nucleophile as well. So in that way, any kind of nucleophile can attack as well this part in here, as well as in here. In this one, we need to remove this hydrogen, but that same base can attack as well in here. So we need to be careful in that perspective whenever we're going to create a synthesis that involve more than one functional group. Maybe we need to protect one of them, and the acetals is going to give us that tool. So we must protect the carbonyl into a functional group that does not react with bases and nucleophiles. Like ethers, acetals are unreactive to bases and nucleophiles. Okay, so remember when we're talking about ethers are really bored. Remember when I mentioned that in class? They don't react with basically nothing. So that's why they're a really good solvents, because you can use them. They're not going to be involved in most of the organic reactions. So acetals are as unreactive as ethers, okay, to bases and nucleophiles. Conversion of a carbonyl to an acetal protect it from base. The acetal is called a protecting group. So now we can take that type of acetal group and use it in our advantage to create a protecting group and protect that part of the molecule. So what we're going to do first, we're going to create first that acetal group. So we have here the diol, ethanol diol, and we're going to create that acetal in here, which is this one. Okay, this is the keto of reactant, and that one is going to protect the carbonyl group. This is pretty unreactive. This is unreactive basically at all. This is going to react just with acid, but we're going to use basic condition to do the substitution in here. And once we make that kind of we're gonna add now the NaNH2 to remove the hydrogen in here, and then use this to attack this, the allyl alkyl here, to increase the length of that, or do the alkylation of that alkyne. And now we can basically take that acetal in here and the protective by an acid, with acid. So with acid, we break this acetal in here, and we recall again the carbonyl group, and we have this modification in the molecule without affecting the carbonyl group. Okay, so we go through the keto protecting group in that sense, and do the reaction in here as normal. We use the NH to remove the hydrogen, the acidic hydrogen of the alkyne, and then use that as a nucleophile with the alkyl halide. And then we deprotect the keto here to have again and regenerate the carbonyl group. And in that way, the acetal function as that protecting group. So let's go now to section 18.10, reaction with primary amines to produce imines. In this reaction, we're going to react amines with aldehydes and ketones, and eventually the product of this reaction is going to be the imine. So carbonyls react with primary amines. The primary amines are those compounds that has a nitrogen and an alkyl group, just one alkyl groups. Nitrogens, they can have at least 3 bonds. NH3 ammonium is the most common amine that we have, NH3. So one of each of those hydrogens can be substituted by an alkyl group. If you substitute just one, NH2R, that's going to be a primary amine. And when we have amines that react with carbonyl groups, the product is going to be imines. And this is going to be a two-stage process, two-step process. One is going to be the nucleophilic addition of the amine, primary amine, across the carbonyl group. And then you're going to have the elimination of water to eventually obtain the imine. And we're going to see that in the mechanism in a few slides. So the imine formation is generally reversible, but can be driven forward by removal of water. Basically, it's an equilibrium type of reaction. And we can manipulate that by removing water. We're going to move toward the production of the imine. In that sense, we're going to favorite that position. Know that the amine must be primary to produce the imine. So here we have an aldehyde. We have the primary amine, as we mentioned before. We have an alkyl group, NH2. So one of the hydrogen was substituted by this alkyl group. And the addition is going to basically add to this carbon of the carbonyl, and then the O is going to convert or produce the OH. This species here is known as a hemiaminal. And then this hemiaminal is going to eliminate the water and produce then the imine. This is basically the double bond carbon is known as the imine. So the hemiaminal in here is going to eliminate this water, okay? And then create a double bond between the nitrogen and the carbon. And in that way, we can produce the imine. And also we remove this hydrogen from here with the OH to produce the molecule of water, okay? So that's the reaction of the primary amine to produce then imine. The mechanism, the first step is going to be the nucleophilic addition of the amine to the carbonyl group. We have here the amine, methylamine, attacking the carbonyl group, which is the electrophile in here, nitrogen, 2 lone pair of electron, good nucleophile, attacking here. And then we break this bond to create the lone pair of electrons and up here. And this is the dipolar intermediate that we have. Then we can do a proton transfer between the hemiaminal intermediate, to produce the hemiamino intermediate, we can remove this hydrogen from the primary amine with water, and then we can protonate this oxygen with a molecule of water. Okay, yeah, the same way as we deprotonate this nitrogen, we're protonated this oxygen to create eventually the hemiamino that is going to be our intermediate. So we have the OH, and we have the nitrogen from the primary amine attached to this carbon. That's a new bond, nitrogen carbon. Then the protonation of the hemiamino oxygen. Okay, we can protonate this, creating a water, which is an excellent living group once again. And the intermediate is now poised to lose water and a proton to form the imine product. So the elimination of water, okay, we remove water, then this lone pair of electrons is going to create a double bond of carbon nitrogen, and then we remove the molecule of the atom of hydrogen to produce the imine. So here we have the double bond carbon nitrogen, the hydrogen, we remove that with water, and we create a lone pair of electrons in here to produce the imine in there. So we have here the N-benzyl, the methylamine, and we have the hydronium ion in here, molecule of water in here. So this in here is the imine that's a product of the reaction. So also we can do the same type of reaction with secondary amines, okay? But it's going to be a different products. So the nucleophilic addition of primary amines to carbonyl groups are going to produce the imine, okay? That is basically the carbon double bond nitrogen, the imine. If we use a secondary kind of amines, we're going to produce an enamine. The enamine basically is a double bond carbon-carbon with the addition of the nitrogen with the amine, secondary amine, okay? So this is an enamine. So we have the aldehyde in here with a secondary amine. We produce an hemiamino in here as well, and then we do the elimination to create the double bond. We're going to go over that in the next slides. So nucleophilic addition of 2 degrees amine, so it's going to be a secondary amine. Secondary amines have no hydrogen to eliminate after the addition cross of carbon. Remember, when we add the amine to the carbonyl group, we have 1 hydrogen in there that when we produce the enamine, we remove that hydrogen. In secondary amine, we don't have that. That's why we don't produce the enamine. We produce the imine, the imine. We can produce the enamine that we're going to create a double bond carbon-carbon. So here we have the aldehyde with the secondary amine. That secondary amine is going to attack and create the same kind of intermediate as we saw before, the hemiamino, that is this one, the OH with the nitrogen. But now, instead of create a double bond between this nitrogen and carbon, we're going to create a double bond in here through the elimination of water. Okay? So the elimination of water is going to create a double bond between carbon and carbon instead of carbon-nitrogen as we saw with the primary amine. So in this case, we're going to produce an enamine. Okay, the enamine is going to be the double bond with the nitrogen and the 2 alkyl groups, the enamine. Instead, elimination of water across the carbon-carbon occurred to give double bond carbon-carbon adjacent to the amine group and enamine. Okay, so that's the enamine. The enamine is a product of the secondary amines with the carbonyls. The imine is going to be the product of the primary amine with a carbonyl. Okay, that's basically the wording. Primary amines with carbonyls create the imine, and secondary amines with carbonyls create the enamine. Enamines are mildly nucleophilic at carbons, making them useful for carbon-carbon bond forming reactions. So the mechanism of enamine formation, as for the 1 degree amines, the primary amines, the first step involves the formation of an hemiamino. The hemiamino expels water to give a resonance stabilized iminium ion. So this is already the hemiamino, okay? And basically we produce the double bond carbon nitrogen to give the iminium ion. The protonation of the alpha position gives the enamine. So now we remove one hydrogen from here. Okay, the hydrogen from here that we have in here, we're going to remove it and create a double bond between here, this carbon and carbon, and then put this 2 electrons in the nitrogen to stabilize that positive charge. So the water is going to remove this hydrogen, creating the double bond between carbon-carbon, and the previous double bond of the iminium ion is going to create a lone pair of electron on the nitrogen, creating then the enamine. That is this one here. We have the double bond attached to the nitrogen, to the nitrogen of the amine, or the amine, basically. This is an amine as well here. So this is an amine with a double bond attached. So in summary, nucleophilic addition to aldehydes and ketones. Hydration. This hydration can be acid or base catalyzed. The product is going to be geminal diols. This equilibrium is normally unfavorable for ketones unless R or both are strongly electron withdrawing. Okay, remember the ketones, those alkyl groups are going to add electron density, but if we have some kind of atom or part of the molecule that is electron withdrawing, that's going to make that carbon a good electrophile. But normally the ketones are less reactive than aldehydes, and that's why the aldehydes are more hydrated when water than the ketones. Cyanohydrin formation. This reaction is catalyzed by cyanide ion instead of the acid cyanide. Acetal and ketal formation. This reaction is acid catalyzed and proceeds by way of hemiacetal or hemiketal as intermediate. And the reaction with primary amines, isolated product is an imine formed by the dehydration of hemiaminal intermediate. And the reaction with secondary amines is going to produce also a hemiaminal intermediate that cannot give an imine because they don't have the hydrogen in the nitrogen. So they remove the alpha hydrogen and they do dehydrates the molecule, producing the carbon-carbon double bond in that sense. And that's going to be the enamine product. So the last section of this chapter 18 is going to be covering sections 12 to section 18.12 to 18.15. The Wittig reaction is going to be the last nucleophilic reaction that we're going to see for the carbonyl groups. Then we're going to talk a little bit about stereoselective addition to carbonyl groups, oxidation of aldehydes, and finally, we're going to talk of spectroscopy analysis of aldehydes and ketones. We're going to talk about the main, more important type of signals that we're going to observe in NMR as well as infrared. So, Wittig reaction. The Wittig reaction involves the synthesis of alkenes from carbonyls and phosphonium ylides. So in this reaction, we have a carbonyl group that is going to be converted to an alkene. Okay, this is going to be the Wittig reaction. So we have something like this. This is the retrosynthesis. We have here a double bond, an alkene. So this alkene can come from an aldehyde or a ketone. And this is the sulfonium ion that is going to bring this part in here. That is this part of the double bond. Okay, so we can, one part of the double bond is going to come from the aldehyde or the ketone, the carbonyl group. And the other half of the double bond is going to come from the phosphonium ylide. The ylide, like carbonyls, both nucleophilic and electrophilic. Okay, they are nucleophilic, as you can see here. You have let me remove the thing in here pretty quick. So you have in there, you have in here that negative charge, there's a positive charge. So that means that this is a good electrophile, a good nucleophile, as well as this one. Here, this is good nucleophile, and this is a good electrophile, okay? So as the same as the aldehyde and ketone, the alide, they have a nucleophilic and electrophilic part. So that's just this. So eventually we can create a double bond in there. And we need to have in mind that this phosphorus is an electrophile. This carbon is a good nucleophile. The nucleophilic ylate carbon bonds to the carbonyl carbon because the carbonyl carbon is going to be is an electrophile. So this nucleophile attack the electrophile, and that's where you have that double bond between carbon and carbon. That eventually is going to form that carbon double bond carbon. So the preparation of phosphonium halides. To prepare phosphonium halides, phosphines are first reacted with alkyl halides to form the p carbon bond. So we have here triphenyl phosphine react with when any kind of alkyl halide, the one that's going to have the two R groups for the double bond eventually. And then it's going to be a nucleophilic attack. We have the X as a good living group. And here we have the halide, the halide, the triphenylphosphonium halide. This one is going to eventually use a conjugated base of dimethoxy sulfates to remove this hydrogen and create the halide. That is this one here. The halide that is going to react with the carbonyl group to create the double bond as the final product. So we have here the carbonyl group. We have here the phosphonium ion. This CH2 is going to substitute the oxygen in here, okay, to create the alkene. That's our main product. And we're going to have here the phosphine oxide. This oxygen from the carbonyl group is going to replace the CH2 or the alkyl group that you have in here in the halide, okay? This reaction is driven by the great strength of the PO bond. The mechanism involves cycloaddition followed by retrocycloaddition. So the first thing that happened in here is that we're going to create a cycle, okay, between these two. Remember, this is the nucleophile in the halide. This is the electrophile. In the carbonyl, this is the electrophile, and this is the nucleophile. So the nucleophile here is attacking the electrophile. The nucleophile in here is attacking the electrophile, and you're going to have this type of intermediate, okay? And then this bond between the phosphorus and the carbon is going to create a double bond between carbon and carbon, and this bond between the oxygen and the carbon is going to create a double bond between the phosphorus and the oxygen, and there we're going to have our alkene as our main product. So the main point in here is you're going to use the phosphine in here. Anything that you have here as an alkyl group is going to be attached to the oxygen, creating then the alkene as a product, okay? And as well here, this part is going to be this side of the alkene as well. So whatever comes with the aldehyde or the ketone, that's going to be this side of the alkene, and whatever comes from the phosphine is going to be this part of the alkene. 1813, seroselective addition to carbonyl groups. Chiral ketones and aldehydes have two distinct faces, above and below the carbonyl group. Addition usually occurs selectively at the least hindered phase. So here we have this compound, which is a ketone, bicycle ketone. And in the presence of NABH4 with isopropyl, we have this product in here. NABH4, sodium borohydride. This hydrogen acts as what? The hydrogens in the sodium borohydride. Remember, those hydrogens are H negative. They have two electrons, a lone pair of electrons. So they are nucleophile. Those hydrides are going to attack the carbon. That's why you have the hydrogen in red in here. They attack the carbon of the carbonyl. The carbon of the carbonyl, once again, is an electrophilic part of the carbonyl. So it's going to be attacked by the hydride. And that hydride can attack from the bottom or from the top. As you may see in here, there's a lot of endurance in the top. So it's going to be harder for them to attack from the top than from the bottom. And the yield, 80% is this product, 20% is this one, because it's more easy for them to attack from the bottom. It's less hindered. This sense of addition is both kinetically and thermodynamically favored. So basically we have here the same thing. The approach of borohydride from this direction is hindered by the methyl group. And this one is going to be more easy. There's no thing that can basically block the attack of that hydrate from the bottom. In our body, we have a lot of different chemical reactions that involves, for example, carbonyl groups, reduction and oxidation of them. So enzymes, for example, catalyze the enantioselective addition of nucleophiles to carbonyl groups. NADH, once again, hydrate here is going to reduce, is a coenzyme that help in the reduction of pyruvic acid to lactic acid. So this NADH is going to attack this carbon in here, producing the alcohol, and this is going to be the lactic acid. The enzyme that they use is lactic dehydrogenase that we use in our body, and eventually we're going to produce, again, the oxidized form of the coenzyme, that is NAD, that reduce these ketones to the alcohol. The chiral environment of the enzyme shields one phase from the nucleophilic attack. In this case, basically, both sides are flat, so they can attack any of those phases. However, the enzymes are really specific, and they're going to produce always, in this case, the lactate dehydrogenase, they're going to produce the S enantiomer always, okay, in the case of the enzyme. Also, the aldehydes, as we mentioned at the beginning, can react with oxidative condition to produce carboxylic acid. So, for example, aldehydes are oxidized to carboxylic acid by chromic acid, H2CrO4. Aldehydes come from primary alcohols, remember? So to create primary alcohols, to create aldehydes, we can use primary alcohols using mild conditions of oxidation, PCC or PDC. Once we have that aldehyde, we can have a lot of different ways to go. If we need to produce a carboxylic acid, we can use stronger condition as chromic acid that would oxidize this aldehyde eventually to the carboxylic acid, okay? So furfural, that is this aldehyde in here, under the chromate acid, chromate salt in this case, the chromate potassium, is going to basically produce the furoic acid, the carboxylic acid. So the aldehyde under oxidative conditions, this is the product, the carboxylic acid. The hydrate aldehyde, geminal diol, is likely involved in this process as well. Okay, so we can produce here the O water is going to tag in here, creating the geminal diol, and then eventually the oxidation of one of them to create the carboxylic acid. Because the hydrate is more reactive than an alcohol, any aqueous oxidation condition will convert the alcohol to the correspondence carboxylic acid, okay? Because the geminal diol is going to be really reactive in that case, and it's going to be really easy to oxidize. Also, we have some biological reactions in our bodies. Aldehydes are converted to carboxylic acid by aldehyde dehydrogenase enzyme. So once again, we have the NAD that acts as the hydrate acceptor in this reaction, and water is the source of hydroxide molecules or ions. So ethanol, in the presence of alkyl dehydrogenase, is going to be oxidized, and we're going to have here the aldehyde. But this acetaldehyde is pretty dangerous. So our body oxidize this to the corresponding carboxylic acid, which is acetic acid. So alcohol dehydrogenase produce the acetaldehyde, and then aldehyde dehydrogenase produce the acetic acid. The body uses a dehydrogenase to convert toxic acetaldehyde into harmless acetic acid. So those chemical reactions that we learned today about the oxidation or reduction, they also happen in our bodies in different kind of reactions. Finally, 18.5, spectroscopy analysis of aldehydes and ketones. Infrared spectroscopy, aldehydes and ketones give a very strong characteristic peak between 1,710 and 1,750 centimeters -1. And aldehyde carbon hydrogen stretch also appear in spectra of aldehydes, is around 2,720 and 2,820. So this is butanol, and this is the IR of butanol. This strong peak in here is a stretch peak of carbon double bond oxygen. Okay. All the peaks are below 3,000, so we don't have insaturations in that case with this group. But we have these peaks in here. These peaks are pretty characteristics of the aldehyde. Okay, so these peaks in here are characteristic of the stretch of the carbon hydrogen of the aldehyde. That's for the infrared. So we have this peak and we don't have this peak. What do we have? If we have this signal and we don't have this signals, we have then what? Very good, a ketone, okay, a ketone. And the proton NMR, basically the aldehyde proton is highly shielded. It's going to be between 9 and 10, and it's very characteristic. It's going to be a singlet down there. Alpha protons and aldehydes and ketones are the shielded relative to alkane protons, so it's going to be between 2 and 3. So this is 2-methyl propanol, okay, 2-methyl propanol. We have these two are equivalent. So we have here an integration of 6. Here we have an integration of 1, and here we have an integration of 1. This basically is the signal for that one is in here. We expect it to be a doublet because we have just one neighbor, okay? This one should be a multiplet, as we see here, because it has 6 protons neighbors, and this one doesn't have neighbors, so that's basically our last peak of the spectrum. It's a singlet. It is between 9.5 and 9.7, between 9 and 10, okay? This signal here is going to be the signal for the hydrogen of the aldehyde. And the rest basically is the same thing that we have been looking before. This is the shielded, so that's why basically is an upfill, and this one is going to be a downfill. This one is going to be upfill compared with this one is more shielded than this one because of the distance from the carbonyl. The carbon-13 NMR is pretty similar as the concept as the hydrogens NMR. So the carbonyl carbon appear far downfield for carbon-13 NMR. The carbon for the carbonyl of ketone and aldehyde is going to be basically over 190 or 200. Okay, so here we have that carbon from the carbonyl group is going to be over 200. And the rest basically is going to be basically similar as the effect that we saw with the hydrogens. We have 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7 carbons in here. And this one is going to be the one for the carbonyl group. The rest is going to be mixed in here. And mass spectrometry, we have one possible fragment that is really important other than the molecular ion. The loss of one alkyl radical from that carbonyl also is going to give a fragment that we're going to see in the mass spec. This one here is the molecular ion. Okay, we are going to have, for this case, 3-pentanol is going to be 86. When we lose this fragment, we're going to have, or with this alkyl group, we're going to have a fragment of 57. That's going to be also another really important kind of fragment that we're going to see. So the elimination of the cleavage of those alkyl groups are going to produce fragments that are going to be really important in the mass spectrometry. So the Wittig reaction is the reaction of a phosphoryl ylide with an aldehyde or ketones, and it's a synthetically useful method for the preparation of alkenes. Okay, the alkenes, we can use the Wittig reaction, which is a carbonyl from aldehyde and ketones, and the phosphoryl ylide. Also, nucleophilic addition to the carbonyl group can be seroselective. When one direction of approach to the carbonyl group is less hindered than the other one, the nucleophile normally attacks at the less hindered phase. Okay, so that's going to be my main attack phase is going to be the less hindered. Aldehydes are easily oxidized to carboxylic acid under any kind of oxidative conditions. And in the spectrum part, the IR, you have a strong peak between around 1700. That's going to be for the stretch of the carbonyl group. And also we saw the two possible signals that we can have for aldehydes below the 2000, around 2700 and 2800. In the NMR, the hydrogen and carbon, the hydrogen for the formyl group is going to be between 8 and 10, is going to be really, really downfill. And the carbon of the carbonyl group and the carbon NMR as well is going to be around 200, really downfill as well. So that's going to be it for chapter 18. And next week, we're going to start chapter 19. Have a good one. God bless you all.